All right, so let's talk now about product and quotient rules. So let's say we have the functions f at x and g at x, and suppose that these are nice differentiable functions. And of course, what's something we're often going to want to do? Well, we're often going to want to take their product or their quotient. So let's maybe call h of x be their product, and maybe k of x be their quotient. So a natural question, I'll write it over here. Question: what are h prime of x and k prime of x? Now, you may note that I'm not drawing a picture here. And why am I not drawing a picture here? Because frankly, a picture wouldn't help. I drew the pictures just to get an idea to put the concept of lines in your head in the previous video, because there, with sum and constant multiple, you can sort of think about where these rules are coming from. But the rules, the product rule, which is going to be for the product, and the quotient rule, which is going to be for the quotient, they're things that you can work out directly from the definition, and I invite you to do so if you'd like. I'm going to omit that for this video. But they are going to look a little stranger, and they're not as straightforward. Nonetheless, it is what it is. We have these rules, and functions, obey various rules. Everything has to work together. So in order for everything to be consistent, sometimes we need a couple of strange formulas. And indeed, these are the strange formulas in this case. So the product rule is the following. It is the case, and can be checked from the definition, that h prime of x is going to be equal to f at x, g prime at x, plus f prime at x, g of x. So notably, it is not just f prime at x times g prime at x. That's not a terrible guess, but it's just not going to work out. If you go through the definition, figure things out from there, there's a little bit of a trick to it. You get this fact here. But note, this is pretty easy to compute. What's great about the product rule is we can still very easily compute the derivative of h, so long as we know f, g, the derivative of f and the derivative of g. So in terms of the information we need, this is not too heavy, it's not too taxing, but it's a little more complicated than you might initially expect. Still, this is the product rule. And similarly, we have the quotient rule, and it's even messier still, but it's still very user-friendly, still something that you can just plug information into and get your answer. We have that the derivative of the quotient of these functions is given by g of x f prime x minus fx g prime of x all over g of x squared. And this is if g of x is not equal to 0. And if it is 0, we're usually going to get this derivative not existing. So basically now what we have here is, this is a bit of a messy formula, something that students get tripped up with all the time, and you'll just have to jam it into your head, is where this minus sign goes. Does it go here or here? But the upshot is, again, just like with the product rule, you can figure out what the derivative of the quotient of the functions f and g is just by knowing f, g, and the derivatives of f and g respectively. So this is pretty good. We like this. Now let's go through some examples. So all right, let's do an example with the quotient rule. So let's say that we have h of x is equal to 1 over x squared plus 1. So this isn't that monstrous of a function. You could plug this into the definition of the derivative, and you can compute it out. It wouldn't be too bad, but it is going to be a little arduous. I recommend you do give it a try, but after giving it a try, you can loop back and see it's a lot faster if we use these nice derivative rules, and that's why we like these rules in the first place. So how are we going to differentiate this? Well, let's call the guy upstairs f at x and the guy downstairs g of x, just like we previously did. And then by the quotient rule, we have that h prime at x, well, it's going to be the derivative of the top guy times the bottom guy minus the top guy times the derivative of the bottom guy all over the bottom guy squared. So now we can just plug everything in. Indeed, in this case, we have that f prime of x, well, f at x is just 1, so the derivative of that is going to be 0. And also downstairs, g of x, that's just a polynomial. We saw last video how to differentiate polynomials. The derivative of this guy is just going to be 2x. So now we can just plug everything in. This first term goes away because we're multiplying something by 0, so we can just omit this term. So we have minus, well, 1 times g prime at x, which is of course just 2x. So minus 2x upstairs, all over x squared plus 1 squared downstairs. And with this function, the denominator is never 0, so this is going to be differentiable everywhere. So this is a nice example with the quotient rule, and we've differentiated this function. Now, let's talk about something slightly different and do sort of a more theoretical example with the product rule. Well, one thing that you might hope to do, and this is how in my last video series we talked about talking about limits, is you might want to sort of think about how derivatives work by going with just sort of very basic pieces, starting by saying, working with the functions 1 and x and finding their derivatives respectively, and then building things up from there with rules like how to add derivatives, how to multiply derivatives by constants, and how to take the product of functions and find the derivative there. So in principle, what one could do is one could start with the derivative of x and then use something like the product rule to find out what the derivative of x squared is from there, and then x cubed, x to the fourth, x to the fifth, and so on. So let's talk about just how one would do that. And another thing is, this is also going to show us why the product rule sort of has to have this strange form, because it has to play ball with things we already know. So indeed, we already know that if f at x is equal to x to the n, we've computed already that f prime at x is equal to n times x to the n minus 1. But what's another way that we could have computed this other than by direct calculation? So let's just say, suppose we know for gx is equal to x to the n minus 1, that g prime of x is equal to n minus 1 x to the n minus 2. So suppose, for example, we want to find out what x to the 7th is, and we've gone through all these calculations, we've already figured out what the derivative of x to the 6th is. So how can we use our knowledge of the derivative of x to the 6th to compute the derivative of x to the 7th? Well, we can do so as follows. So if we have f at x is equal to x to the n, and g at x is equal to x to the n minus 1, note that we have that f at x is equal to x times g at x, because indeed x to the n is equal to x times x to the n minus 1. So by the product rule, we therefore have that the derivative of this guy is, well, it's going to be the derivative of x, which is 1, times g of x, plus x times the derivative of g of x, which is going to be x to the n minus 1 plus x times n minus 1 times x to the n minus 2. But x times x to the n minus 2 is x to the n minus 1. So this is x to the n minus 1 plus n minus 1, x to the n minus 1, which altogether is what we want, n times x to the n minus 1. So this is a little theoretical, but indeed, what was I saying previously? The product rule and quotient rule, they look a little strange, but there's a lot of things going on. They have to be consistent with everything else. We knew that the derivative of x to the n was this, but this has to be consistent with the product rule. That is to say, if f is x to the n and g is x to the n minus 1, then f is this product of x times gx. So the derivative of f has to play ball with the product rule. And this is just that in action. So hopefully this gives a little sort of spark of an idea as to why these rules have to look a little bit stranger, just because they have to make things that we already know work and be consistent with everything else.